Welcome everyone to this webinar. Here is a very short introduction to the overall project. The goal of BDE is a support action which integrates well into the open data strategy and big data value chain strategy that of the European Commission, because Europe wants to be a digital economy and they were missing bricks like an easy to use platform. But as you will see in this webinar, BDE performed beyond that goal because there are key innovation points. Especially, I put your attention to the semantic lifting and the parallelizing of the processing of linked data. So as a preview, Simon, who is the technical coordinator of the project, will give you a short introduction of the overall project. Hajra Jabin will introduce the architecture and the features of BDI, the Big Data Integrator or BDE engine, and explain the easy-to-use UI on top of it. Ivan Amilov will tell you how a BDE imagines the Stack's lifecycle, how to create your big data project. And Art Versteden will then demonstrate the BDI. Let's cross fingers that this will work without hiccup. And Jens Lehmann will provide one of the key innovation points of the BDI, the semantic analysis stack, also known as SANSA, that is already used by other projects. Finally, Ronald Siebes will present the individual implemented pilots with interesting insights, and Luigi Selmi will then present one of those pilots on transport. And at the end, our coordinator, Simon, will draw conclusions, present uptake, and we'll take, we'll have a short question and answer session moderated by Simon and me. So have fun with the webinar.
Thank you, Rigo, for the introduction. So let's start. And the first part of the webinar is a summary of the activities from the project. So as you probably know, the Big Data project was a coordination support action starting exactly, well, 3 years ago. We're in just before the last month of the project, at which point, of course, most of the results are mature, if not completed. And just a bit of a background again. So the point of the project funded by the Commission H2020 is to talk to the stakeholders for big data. So users of big data, people who would need big data technology, or people who own big data, to get them together within this different communities aligned with the 7 societal challenges, see what their needs are, their challenges are, collect requirements, see what's missing in terms of big data technology platforms, and try to make basically life easier for everyone. And this is the support side. So there's the coordination side and the support side. You can see a little map there with the 16 different partners in the project, quite a large consortium. And as I said, like the 2 results and measures and the results of the project are basically split around coordination, getting people together, seeing their needs, requirements, what's missing, what are the challenges, and on the right-hand side, the support. So how the requirements then translate to technical contributions results, namely the Big Data Aggregator platform, which is the subject of today's webinar. Today, again, is the final release within the lifetime of the project. It's the 3rd such release that we have, and we'll present you also the new additions since the last one in spring this year. And again, this I'm very fond of this picture because it gives a bit of an idea of the need for this project. So different domains, different kinds of data, and entities were busy creating their own big data pipeline solutions technology. The big data landscape is very confusing, very large, many different components that can be used. And people were making their own solutions. And this was the wrong approach, because at the end, people or entities have different data, they have different needs or objectives, what to do with the data, but the solutions tend to be quite similar. So the point of the project was to kind of bring all these different data and objectives together to create something which is a bit more uniform and provide a base architecture for a platform which can then be customized for different solutions. That's where you can see over time there on the right, going down to open source solutions even for big data stacks using existing big data components. So not reinventing the wheel. So before we go on to the more interesting sessions, I would just like to remind you that this webinar offers the functionality to ask questions. So everyone attending as a participant, you can ask your questions, and at the end we'll have 10 minutes where we will try to answer well, at least most of the questions. So you can look at them, especially if you're using the plugin, but also through other means, but you can write your questions there and we'll deal with that at the end of the session. So please keep that in mind. If you have specific questions following parts of the webinar, you can also address the people presenting, but otherwise we'll channel them to the right person who can give you the best answer. So thank you very much for the introduction. I will now call for Hajra, so Dr. Hajra Jabin from the University of Bonn, also the technical team leader, who will continue with the next part of the webinar. Thank you. Hajra, we cannot hear you. I think you're muted.
Can you hear me now?
Yes, all clear.
Yeah, thanks, Simon, and hello and good afternoon, everyone. So I'm Hajra from University of Bonn, and together with TenForce and Infi, we have been working on development of this Big Data in Europe platform. As you already know that there are a multitude of big data tools and frameworks, and that serve as one of the many specialized domains for big data world. But as a novice user, it's not very easy to getting started with these tools. So the main goal of the platform is to make it easy to install, develop, deploy, and integrate all of these components. And it was one of the challenging tasks for us to develop a generic platform that is easy to deploy, use, and is adaptable enough so that we could integrate the new coming tools and processing engines that are being developed at a very fast pace. So after fiddling and after playing with different existing tools like Mesos or Yarn, we finally converged to using Docker ecosystem at the end. And I will briefly go through what Docker is and how the system works. Actually, the Docker is a lightweight visualization tool, which allows you to package one application together with its dependencies. The main aim of Docker is that the application runs as intended, regardless of the host environment or operating system. A Docker file is used to it acts as a template to describe one Docker application. Docker Compose is another tool. Using this tool, you could deploy multiple Docker containers at once. And Docker Swarm is a native clustering tool for Dockers that allows you to bundle different hosts together as a single virtual host. And it acts as a resource manager or cluster orchestrator for multiple Dockers. So the main aim of Big Data in Europe platform was to reuse the components wherever possible and to introduce our own tools wherever there is needed. So while working with Docker ecosystem, we realized that within Docker Compose files, when you try to deploy multiple Dockers at once, it happens that sometimes it is not the intended behavior. And what we want to do, there's sometimes dependencies between one Docker application and other Docker application. For example, in case of HDFS name node needs to connect to the data node. So name node should be running before data node. Similarly, in case of Spark, Spark workers need to connect master. Therefore, master has to be up and running before workers try to connect to it. Or if Spark needs to read data from HDFS cluster should be running before that. So we created a workflow builder that allows you to tell this workflow of different dependent components before creating the stack. So you could tell this pipeline monitor app, workflow monitor app, the intended order of execution of the components. Then we also have an integrator UI. So as all of us know already, that different components have different web interfaces. For example, Spark Master has its own web interface, Hadoop name node has its own web interface, and same goes for Hadoop data node. And all of them, because they are developed by different vendors, they have different look and feel. So what we did within BDE is that we created a unified integrator user interface for all of these components running within a single stack. Then there's also a a semantic analytics components that we would detail later in this webinar. So another nicer thing about this support layer that I just explained is that you could opt out of it. So if you do not want to create dependencies among different running applications and you do not need to have an integrator interface, you could simply opt out of it, which also gives our BDE platform a modular structure where you could choose different components that you want to work with and simply opt out of the ones that are not needed. So this is an alternate view of the BDE platform architecture. In the bottom, you could see you have the hardware layer. On top of hardware, you have the Docker Swarm as resource manager. In data layer, we have multiple frameworks like Hadoop, HDFS, RDF Store, or in NoSQL, we have Elasticsearch, Cassandra, and many more. And then in platform layer, you could have Apache Spark, Flink, or for message passing, you could have Kafka, and there are certain tools developed within BDE like SANSA or Ontario. And then at the left, you have the support layer, which allows you to create stack using these bottom components, using some graphical user interfaces. You could monitor these stacks, or you could create a workflow of these stacks using init daemon. And at the top, you have this application layer, where as a user, you would write your own application that would use the components in the bottom layers to create, to realize a pipeline for your own data value chain. BDE supports numerous components that were required from one of the 7 societal challenges of this platform. Ronald will explain what these use cases are and how they are built. But we have tried to cover a wide range of applications like searching, indexing. We have Apache Solr for that. For acquisition, we have Apache Flume, message passing, Apache Kafka, and many others for different tasks. So what does it mean by supported frameworks is that we offer templates in terms of Docker files, which have init daemon already integrated, or which already have the support components integrated in them. So they are ready to use components. But on the other hand, external or proprietary components can also be easily extended and integrated into BDE platform. So in general, BDE platform offers features like mostly features in terms of user interfaces, like we have a stack builder that allows you to select different components from BDE repository, then workflow builder that allows you to create workflow of those components, and then you also have instructions that you could follow to add custom components to the stack for your own workflow. And for administration of the cluster, you have Swarm user interface and a logging interface, and then for each stack, there is a workflow monitor and an integrated web interface. As a user, the user would have to clone a single repository. Using a web interface, user can select different components, and then he could proceed to workflow builder, where he can rearrange components to state the workflow of running of different components, and from there on, a user can proceed to SOM UI, where they can see the scaling, see different Docker components applications running, and scale them up or down as needed. And a BDE logger that tells the status of different running Dockers on the cluster. And then there is a separate integrator UI and work monitor for each of the stack running on top of this platform. So all of these user interfaces altogether constitute the BDE IDE. So I will now briefly go through one of each of these user interfaces. So this is the Big Data Integrator interface. From here, you proceed to Stack Builder, where you could select different components and create a stack out of them. This is the stack editor. Here you could see that these are the components existing in this stack, and here you could see there are 2 services for Flink or Dockers, or 6 Dockers or 6 services for HDFS, and there is one for store and other for store master. From there, you could go to Workflow Builder. Here you could drag and drop these components forward or backward. So these are, for example, 3 components that you need to create a workflow for. And this is Workflow Monitor. Here you could see the status of different Docker components, and you could see if it's running or if it had finished running, and so on. And this is an interface for SOM UI. Here you could create a new pipeline, or you could edit Docker Compose files for individual stacks. And this is the pipeline. Here you could see the services running. You could scale them up or scale them down as needed. And this is the interface for the logger. It uses Kibana and Elasticsearch. And this is the integrator UI. Here you could see that there are different components running. For example, we have Spark, Spark Workers, Spark Master, HDFS, and Virtuoso running. You could navigate through these different tabs to visualize the web interfaces of these individual components. So when we try to compare Hadoop with, BDE with other Hadoop distributions, you could see that BDE also uses HDFS for storage, but installation is lightweight visualization, so you don't have to natively install all of the components. At the same time, it has a flexible modular architecture, so you do not have to install each and everything all together on your machines. It is it's free of cost. It has scaling that is offered by Docker's Swarm itself. It works on many different distributions of Windows, Mac, Linux, because of the use of Dockers. And for management, we offer Docker Swarm user interface and some custom interfaces. So in conclusion, BDE is not built on top of existing distributed frameworks, and it targets to facilitate communities, research institutions. And what we are trying to do is to bridge the gap between scientists and open data, or bridge the gap between data and tools that exist to analyze and process their data. And it is a multi-tier research efforts towards smart data as well. So you would come to know in more detail later in this webinar. So now Ivan Ermolov, who's core BDI developer, would explain the Big Data Integrator Lifecycle interface.
Thank you, Hajra. Let's switch over to Ivan.
All right. Hello, everyone. All right. So I'm going to present the lifecycle, and it's basically about how to develop the big data applications using the technologies which was presented by Hajra previously. In the Big Data Europe project, we basically systematize the knowledge from societal challenges and development experience we had in the project and develop a methodology for the big data application on top of the Docker ecosystem. It looks like this. It basically has 6 steps. As you can see here, it's development, packaging, composition, and enhancement, deployment, and monitoring. So it iteratively go in cycles, and it basically supports the agile development. You can start with putting together several components, and whenever you go for the further developing your application, you can add Kafka or Hadoop, etc., etc. So you can add new components and develop it in an agile way. The initial step here is development, where the big data frameworks and custom applications for data processing are put together. Then the packaging is where the developed components are enveloped into Docker images. On the composition step, a single BDE stack is assembled. Then on enhancement step, basically, where we have the big data stack, we enhance it with Big Data Europe tools, which we developed inside the project, like an daemon and integration of the user interfaces. You're going to see it further in a presentation given by Art. And then it's deployed using either the basic deployment tools or using the Swarm UI. And after that, you can monitor it. And whenever you catch bugs, you go to the first development step and go again in the circle. All right, so what is a big data stack? It's essentially big data application, and we're not talking only about the application implementing the business logic, but we're talking about all the components like Spark, Hadoop, etc., packaged into one package, which is a Docker Compose definition here. So essentially, it's a Docker Compose definition where everything is defined, and it can be deployed with one command, also on a developer's machine or in a cluster. So let's take a look more closer on how to create those BDE stacks. The first step is to develop the custom applications. And here we provide the templates for Spark and Flink applications, for example, so you don't have to think about how to start. Here we also have a blog post on development for Spark applications. And the cool thing about the Big Data Europe components that you can reuse it for development as well as for deployment. They work the same way, except for you need to provide the configuration, custom configuration for cluster. For the packaging step, you basically take the developed custom applications from the first step, and you need to pack it into Docker images. Also, here is the step when you might have to package custom Apache frameworks, like we already did it for you for Apache Spark, Apache Hadoop, Apache Flink. However, you might want to package, for example, RabbitMQ, and to deploy together with your custom application to reuse it, basically. And this is possible here because we're using Docker as a backend technology. This can be done quite easily. And in case of RabbitMQ, you just need to go to Docker Hub, grab the image, and use it. So on composition step, you need to take all those images you prepared on packaging and put them together into one Docker Compose file. You can do it manually. You can go through the GitHub repository we have. It's called Big Data Europe on a GitHub. You can copy paste the Docker Compose snippets, or you can use Stack Builder user interface, which Art will present a bit later. So when you have your Docker Compose YAML file, you want to enhance it with a custom Big Data Europe applications, and they are aimed to solve some problems we encountered inside the project. Like there is an daemon which basically ensures the startup order of the components. We have a problem when if you start the data node of Hadoop before the name node, data node will not connect to the name node until you restart it. So that problem can be tackled with any daemon. And there is, of course, integration of user interfaces and interfaces for monitoring, which you want to put inside the stack. So for deployment, you take the Docker Compose YAML file you will have after that, and you basically deploy it in a cluster. You can do it using Docker Stack deploy command from the last Docker Swarm mode, or you can use a Swarm user interface, which we provide inside the project. On the last step, you monitor the cluster, and we developed an application to monitor HTTP logs, and it's also available into the IDE, which is going to be presented a bit later. And you can log, you can monitor the logs from the framework separately, like you have Spark and Hadoop and whatever you deploy there, and see if there are any bugs, and then you return to development. All right, so that's briefly the life cycle. There is also a research paper on that topic published on KSW conference this year. You can read it. There are a bit more details on that. And a few more words on platform installation. It's extremely simple. Basically, it can be installed on any servers or VMs, and the only thing you need to install there is Docker. So we provide manual installation guides and installation using Docker machine, and also screencast for that. This all is for the old Docker Swarm, and for the Swarm mode, you can refer to the official installation guidelines. It can be installed from the repositories for most of the Linux distributions, as well as Mac or Windows. Okay, that's it. Thank you.
Thank you. Thanks, Ivan, again for that nice overview of the life cycle. And we will now switch to Ad Versteden from lead developer of BDE, and he will give us a demonstration. So let's now switch to Ad.
Hello, can you hear me?
All clear.
Very good. I'm Ad Versteden, currently working at Red Pencil, and I'm here together with Jonathan Langens from TenForce, and at TenForce we have built the Big Data Integrator user interfaces. This is a set of user interfaces that helps you in maintaining your big data lifecycle, say. We support some of the components there, and I'll go through the user interface and through some of the components of the user interface to where it makes sense, it seems. It's going to be a brief overview. We don't have an infinite amount of time. All right, so normally what you'll want to do when you get started with something like big data or with any sort of application, you'll want to try something out. So I'll do the exact same thing and start here. I've just opened the Big Data Integrator, as we call it, and I've opened the Swarm UI itself. Here I have an overview of certain stacks. There's one example here, but we will create a new stack for something that already exists. I can give the name, say that we have a people catalog that we want to have. I think person is an icon that exists, and I can use that icon. Now, where will I find something like this? If we go to Big Data Europe, for instance, there is a project called WebCat, which is forked from another repository. I can just literally take the clone URL that's in here. I can copy that and paste it in here. That's all what needs to be done for this to technically work. I can create this stack. Now, what does a stack really mean? A stack is something that has been built that represents a repository or a place which has a Docker Compose file. Say that I go here and I edit the Docker Compose file, then I can see which things are included in here. Oops. So anyway, I can, as it goes with demos, refresh for a second. I can edit this Docker Compose file, and I can see all of the things that are included in this Docker Compose file. This contains all of the portions that are necessary for this stack to work, and it has a set of related workflows potentially and a set of related stacks. In our stack, we can launch a new pipeline from this stack, and that is literally one instance of such a stack. I've already clicked the button, and there you can see that we have a people catalog here, and that has nothing really included yet. I have a similar service here, which is down right now, and that also has a set of services. As you can see, this one has a set of services, and this one has a set of services as well. Say that I'll go to the stack builder. I want to see what components are in here. In the stack builder, there's a bunch of examples, and it seems we're having a glitchy connection to the server here, but probably still have a backup here or there. What you can see for a larger component like demo Spark sensor data, it contains a wider set of services. This wider set of services is, of course, slightly harder to maintain. And as Ivan earlier said earlier, at some point we need to decide what needs to run at what point in time. That's what we call a workflow. The workflow builder, which is here, you can always click through them between the interfaces. If I open the workflow builder, in which we again have a network glitch, it's just time. What you see here is that we have a set of components, and sometimes you need to decide what needs to run where. Now, you can do this with health checks for a large portion of these things, but not everything. Some things are less expressive, it seems. Anyway, it's a very simple interface to order particular components to say what needs to run where. You can add steps if necessary, and you can then link them to your Docker Compose file in the stack builder. This is a larger Docker Compose file. As we said earlier, it may be that you have small things, and for our example, we'll try to launch something smaller, of course. I can go to the pipelines which exist, and again, we're having a slightly slower connection than we normally have to the upstream, it seems. But what I can do, I'll launch one of these components. When I press up, what will actually happen is it'll start downloading each of these items which should be running in here. It'll download all of them. Each of these services will then be started, and everything will be started in the order what is requested by the workflow builder. Now, this doesn't have a particular order in which it needs to run, but it will run now. This was down earlier when I pressed refresh. If I start it now, then I should get content. And as you can see, there's an application running here now. I can perform various calls in this application, but we're not going to demo the application in particular because that's not of real interest to us. What we will demo still, though, is the network logging. See, when we make a request to each of these components, we actually create a backtrail of calls that have happened beforehand or in between. And we've created a visualization setting of that, being the network logger. The network logger, there's something before here, we'll have to set slightly longer time, say in the past 4 hours. The network logger is an elk stack that monitors each of the calls that go through an HTTP log. As you can see, there's a bunch of logs here, but of course that won't really help us. What really helps us are visualizations that we can have on these. In the past 15 minutes or something, I've created a quick dashboard. We have more extensive dashboards that we use in practice, and we're working on making these loaded automatically. However, what you can see here, if the network gives us the transfer, are 3 different types of viewing user output. And it's hanging now. However, let's go to the discover component for a second again. These are components that we can visualize, and we can start new visualizations based on what we really need to have. Say that I start a new search. I want to know what type of calls that I've made. I can add a terms here, and I can say that I want to have the request method. And this is just literally HTTP that is being parsed. We haven't added a lot into our way of working, but we can see that there's been apparently 12 gets and 18 posts. Now we may wonder what these posts are. When we click this, we will add a parameter here, and now if we go to discover, we will only see the post requests. So it's more easy to discover which things have done what sort of requests. It's also quite easy to enable these things. So if we go back to the stack builder, then if we check one of these stacks, and again the network is lagging, but if we check one of these stacks, the only thing you need to add is a labels true, and from there on everything will be loaded. I think if we try the webcat here, I don't know if I have it open somewhere. I don't. All right, let's look at the Swarm UI, go to the stacks. Let's go to our people catalog that we had earlier. If we edit the Docker Compose file here, then normally what you'll see, which again is lagging, is a set of, it's so sad. You'll normally see swiftly a set of components, and there is a logging enabled. Now, before I host the whole network here and the whole demo starts failing, I will give the work back to Simon, and we'll do a webcast maybe of these particular features and how you can use them in practice with a better network.
Okay, thanks, Adden, and we can proceed for the moment to the next session, which is Professor Jens Lehmann. I will just change directly to my screen again. And we will have a look at the SANSA Semantic Data Analytics stack. Jens is from the Smart Data Analytics department in University of Bonn. And let's switch to Jens. In the meantime, I would like to also remind you that our webinar is recorded, and we will make it as soon as possible available, well, on YouTube and also through our website. And also a reminder to ask any questions in our question bar, and we will deal with that in the last 10 minutes of the webinar. Jens, the floor is yours. We cannot hear you.
So you should be able to hear me now.
Yes, now we do. Thank you.
Okay, thank you for leading over. So far, we've heard a lot about the Big Data in Europe platform as a whole, which includes a lot of generic components which can be adapted to the different use cases. So in some areas, we've also gone deeper in the Big Data in Europe project, and that's specifically the support of so-called knowledge graphs. So I will present two approaches which we have further developed in the Big Data in Europe project, and that's SANSA and the Semantic Data Lake. So first of all, some people may not be that familiar with knowledge graphs. They have developed and became popular over the past decade and are now kind of omnipresent. So the most well-known knowledge graph is the Google knowledge graph, which you can all or which you all use when you use search in the browser. And similarly, Microsoft has their alternative, Facebook, Twitter, LinkedIn. There are also public knowledge graphs like Wikipedia, where we contribute ourselves, Wikidata, Yago, and so on. So those are large-scale graphs which allow to store and extend knowledge. And in the SANSA project, the idea is that we want to bring big data and knowledge graphs closer together. Because so far there are quite a number of tasks which are very hard to perform on those large-scale knowledge graphs. For instance, querying the knowledge graphs and computing statistics, performing quality assessment of large-scale knowledge graphs, detecting outliers, performing inference. That means detecting implicit facts out of the explicit knowledge which is inside of the knowledge graphs. Also clustering approaches, as well as so-called link prediction, so finding out about unknown facts using machine learning techniques. So all of those things are pretty hard to do on large-scale knowledge graphs on single machines. By single machines, I mean machines with less than 1 terabyte memory, which is what you can get for reasonable prices. Beyond that, it gets extremely expensive. So the idea we pursued in the SANSA project is to bring the semantic technology stack, which is used for storing, querying, and inference in knowledge graphs, together with distributed machine learning techniques and APIs. So you can see on the left-hand side here, typical machine learning stack, for instance, for Apache Spark, which I think many of you know. It's maybe the most popular big data framework overall. In those cases, as we've seen also in the previous presentations, you have a distributed file system like HDFS. You have the core computing framework of, for instance, Apache Spark or Apache Flink. Then there are several data structures, distributed data sets which are supported, including streams. And on top of that, they have usually machine learning libraries. So that's what you see on the bottom left. And on the bottom right, you see the semantic technology stack, which consists of a number of standards for knowledge representation and modeling. which were developed over the past 10 to 20 years. For instance, RDF is the resource description framework, and Sparkle is the query language, which is very similar to SQL for relational databases. So we combine those two stacks into a new stack, which we call the SANSA stack. And via this combination, our main goal is to combine the advantages of both worlds. So in the left column, you see kind of the big data processing world, in particular Spark and Flink. And in the right column, you see advantages and disadvantages of semantic technologies stack. What you can essentially see there, to keep it brief, is that semantic technologies are very suitable for modeling knowledge graphs, for integrating them, for exchanging and publishing data. So that's what they've been made for. And those tasks are at the same time very difficult in Spark and Flink. And usually you start from CSV files. You have to find out the structure of the data sources yourself. Integration is often quite a manual process. And yeah, but the main advantage, of course, which you get from those frameworks is that they scale very well horizontally, which is what big data processing is about in many cases. And obviously, they also became popular because you get a direct business benefit. Usually, you perform some sort of optimization or machine learning approach, which directly improves business criteria. So by combining those two worlds, essentially, we hope to retain the benefits of both in the SANSA stack, which consists of those 5 layers here. At the bottom, you have the distributed in-memory processing framework. In our case, we support Apache Spark and Apache Flink. Then we have a layer for representing knowledge and data and distributing it across nodes in a cluster. Then we have a query layer, which allows you to obtain information from the knowledge graph. An inference layer allowing to compute facts out of the explicit knowledge in the knowledge graphs. And then we have a machine learning layer on top, which includes several optimization algorithms. So I'll just quickly go through the layers, and since it's a bit technical, I will really keep it brief, and you can obviously ask questions afterwards or also directly to me after the webinar. So in the lowest layer, we support the RDF and OWL format. RDF stands for Resource Description Framework, and OWL is the web ontology language. So in SANSA, we have interfaces which are very similar to Jena and OWL API, which are the most popular frameworks in this area. However, with the main difference that whenever you read in a very large file, a very large knowledge graph, we automatically distribute it across the nodes in a cluster. And the central idea is that after you've distributed the data, you perform computations on each node in the cluster and then combine data again to get your final results. And this way you can scale horizontally. That means the more machines you add to your cluster, the more efficient you become. So in the RDF layer, in the knowledge representation layer, we support RDF and OWL essentially. So we both support the data level as well as the schema level. In particular, in life sciences, you have very complex schemata, which we can then also distribute to nodes in a cluster. And then on the layer above that, you can answer queries. So here's a short excerpt of how one particular strategy implemented in SANSA works. So at the bottom, you also have some lines of code for the nerds in the audience, which you can use to execute what's shown above. So you start on the left with your knowledge graph, which is stored, in our case, in the resource description framework format. You read this into HDFS, and then you perform a partitioning. So you divide the data in a way that is suitable for performing queries. So in SANSA, you can just select the default partitioning strategy, but you're also free to use other partitioning schemes. And once the data is partition the query layer, it can then access it. And one approach to do this is so-called Sparkle to SQL rewriting. So there we can draw, in this case, on the Apache SQL engine, which implements the core functionality, and we can rewrite our Sparkle queries for knowledge graphs to SQL queries within the query layer. So for instance, with the 4 lines of code shown here, we provide a complete Sparkle compliant endpoint in SANSA. And afterwards, you can also take the results and perform further operations in the framework. Okay, so on top of the query layer, we have the inference layer, which allows to draw implicit conclusions. So for those who are familiar with the area, there are a lot of different modeling languages for ontologies, for instance, RDFS and different fragments of the web ontology language. So we support a number of popular fragments, but the main difference in SANSA is that you can also define your own rule set. So you can define which kinds of inferences you want to draw, and you can kind of define your own rules on top of the knowledge graph, which allows you to be more flexible. Obviously, the more rules you add, the slower the whole process becomes. That's the reason why the more complex modeling languages often do not scale to very large knowledge graphs. So for particular applications, it's a very useful feature to be able to fine-tune the level of inference you need. And from your rule set, SANSA will automatically create a so-called rule dependency graph, which defines how it executes the existing rules. So what the rules do is that they take existing facts from the knowledge graph and derive other new facts from them. So full explanation would be a bit longer, and since we are a bit behind time, I will not go into this in detail. And move on to the machine learning layer of SANSA. So in the machine learning layer, we implement several techniques and also extend this essentially every week. So we support a lot of so-called knowledge graph embedding approaches. So I think many of you know embedding techniques, which have become very popular over the past few years. So essentially, knowledge graph embeddings compute for each node in the knowledge graph, which could be a person, an organization, anything you can imagine, a so-called embedding, which is a feature vector, a vector of numbers, such that similar nodes have similar latent feature vectors. So some of you may know word2vec or other approaches. So essentially, you can transform text, images, everything to those embeddings. And in SANSA, you can do the same for knowledge graphs. Beyond those approaches, we have we support graph clustering. So you can input an RDF graph and compute which nodes belong together and share a lot of similarities. For instance, for visualization purposes, we also support association rule mining. So given a knowledge graph, you can compute if-then rules. For instance, if a customer bought product A, then product B might also be relevant, or similar cases. And we also support an advanced version of decision trees, so-called semantic decision trees. For the knowledge graph embeddings, we include both deep learning-based techniques or neural network-based techniques, as well as so-called tensor factorization in SANSA. What the knowledge graph embeddings essentially allow you to do is to perform several machine learning tasks like link prediction. So given a knowledge graph, you've usually extracted this from some other sources, and the knowledge graph is highly incomplete. So you want to predict further links. A very typical example could be, for instance, recommending friends on a social network. A connection between two persons there is also just a missing link. Essentially, it exists in the real world, but in the knowledge graph, it does not exist yet. So you want to predict, for instance, which persons could be likely friends. So you can solve those problems and a lot of similar problems using those knowledge graph embedding techniques in SANSA. We've implemented quite a few approaches which appeared over the past years in major conference and journals and are used by companies like Facebook and Google. So SANSA is quite easy to install. So if you use, it's written in Scala, and we also work on a Python version now. So if you use a Maven or SBT as a developer, we have default projects there. And you can also run it directly in your browser using SANSA notebooks. And we provide a couple of examples which allow you to get started easily. So overall, SANSA is a very active project. So we perform release every 6 months. So we started inside of Big Data in Europe to specialize on this path, and have now 19 contributors and more than 1,000 commits already in the first year. And we will have another release very soon, I think on December 14th, where you're also invited to check out the latest advancement of our projects. Okay, so SANSA is one project I wanted to cover, and another project I cover a bit more briefly is the semantic data lake. So while SANSA addresses the problem that knowledge graphs can become extremely large, and you want to run them on top of big data infrastructures, the semantic data lake addresses a different problem, the problem of heterogeneous data sources. So often inside of a company, you have several databases, you have lots of different sources where you can obtain knowledge from. They can be unstructured text, they can be wikis, a database, and so on. And it's often desirable to get a uniform view over those. And with the semantic data lake, we support exactly this functionality. So for each of the sources, you can define mappings and perform so-called semantic lifting. And once you've done this, you can obtain a uniform view. So let's have a brief look how this works. So at the bottom here, you can see the different input files. For instance, a relational database, an XML file, a Mongo database, which also have different languages to access them, like SQL, XPath expressions, JSON paths. But in the semantic data lake, the idea is that you want to perform queries which cover all of those data sources. So on the left here, you can see a Sparkle query asking about countries and diseases. And what the semantic data lake engine does is to decompose this query into several parts for the different sources. And then it performs the queries in the particular languages across those input sources. And in a second step, it does result reconciliation. So it gets results from the different sources, combines them, and returns a result according to the Sparkle specification. So from the point of view of a user, you just query it like a single data source, but in fact you can have heterogeneous sources in different formats on HDFS, which you combine. Okay, so I covered two main frameworks: SANSA, our distributed memory computing stack, on top of the BDE platform, and the semantic data lake approach for querying heterogeneous data sources. So I also put some links here to our Git repositories. Everything is under Apache license in case of SANSA. We also have a Twitter account and a website where you can get some more information. Okay, so that's it for the support of knowledge graph and semantic analytics in the BDE platform. And now we will lead over to Ronald, who will show the different pilots for the societal challenges.
Thank you, Jens. While we switch to Ronald, who will give us some information about how the platform and all the technologies behind has been put to good use for 7 different pilots. I would also like to apologize for the network issues we've had during the live demo of the Big Data Integrator, but in addition, we will also, in addition to the recording of the webinar, we'll have a screencast of the complete demo, so you can look at it there as many times as you would like in the next days. So we switch to Ronald now.
Yes, thank you, Simon. So for the people who followed it till now, it might have been, depending on your background, rather technical. And this part of the presentation is to show you what you can actually do with it. And just as a bit of context, so this project was heavily sponsored by the European Union in the Horizon 2020 call. And part of this call was that you have to address at least one of these 7 societal challenges, which I just now abbreviate, which is health, agriculture, energy, transport, climate, social sciences, and security. And it was an ambitious goal of our project, and it got accepted, that we try to develop infrastructure and to help the community, and especially small and medium enterprises and not-for-profit organizations to actually also use all that big data technology, because it's rather a high investment to understand what is all possible and if it's actually applicable to the problems that you have. So where do you start? So one of the main goals of our project is also to make it easier for these communities from all these 7 societal challenges to use this big data technology. So in order to prove that, we had 3 cycles of pilots for each of these 7 societal challenges. So in our consortium, for each of these societal challenges, there is a partner who has a lot of knowledge about that domain. And then they all have a big data problem, and we all work together to develop this Big Data Europe infrastructure that was being talked about before in this presentation. And now I'm going to go over all these pilots and show what is all possible with the technology that we developed in our project. So let's start first with life sciences and health, which is joint work with the Open Fact Foundation and the VU University of Amsterdam. There, the big data focus area is large-scale heterogeneous pharma research data and linking and integration. So if you do pharmacological research, you often have to go to all kinds of Excel sheets and various data sources in order to find connections between targets, compounds, diseases, and tissues. And there are all kinds of organizations who provide information about this, these various topics. And part of this Big Data Europe project, from the Open Facts Foundation, they have linked this all together in semantic web, in RDF format. They have a nice API layer so that you're not confronted with all this complexity of the semantic web. So that is very nice, and that project is run very well. It's well achieved. So now we have a foundation for that. And one of the tasks is all that data which is being linked together doesn't fit on one machine. So you need a cluster in order to calculate, to answer the questions that you might have in this big data graph. So this is actually a big data problem. So if we could decouple the Big Data Europe infrastructure, the Open Facts infrastructure, and run it on our BDE infrastructure, then everybody can add their own linked data and run it in their own cluster. So that is this one. So we have a large-scale RDF reasoning over 3 billion triples, how to have a RESTful API and various front ends. So this is one of the pilots. And for more information, and that holds for all the pilots, please go to the website of bigdataeurope.eu, where you can find information for every pilot. So the second showcase is food and agriculture, which is together with FAO, Semantic Web Company, and Agrono. There, the big data focus area is large-scale heterogeneous viticulture data, extraction, linking, and integration. So in the domain of so viticulture is actually the research about grapes and wine. And in order to make good wines, you have to know a lot about the genes, the phenotypes, the soil properties, climate, and all kinds of data sources, which is kind of similar to the problem in the first pilot in health domain. And the challenge there is to have an infrastructure to combine these various data sources into one queryable infrastructure to help people doing research in that domain. And then also here, extraction was an important part of the pilot, where you have to often go through scientific articles to extract the topics and the images and provide them in an integrated way for the people who do the research. So here the BDE infrastructure tasks are large-scale data extraction and integration, analysis batch jobs to generate statistical data, query support, and various front ends to have a generic overview for that domain. So the third pilot showcase is energy, which is together with CRES and the National Scientist Center for Scientific Research, Democritos. And they're the partner. They have these beautiful wind turbines, and these turbines are very expensive, and they have all kinds of sensors inside in order to prevent, to see that something is not going wrong, because if the gearbox has some sand or salt in it and it starts to rust, it will break down. So if you can prevent that before it completely falls apart, you can save a lot of money. So all these wind turbines, they have a lot of sensors. They monitor all these things, and that's being streamed to a cluster, and then there some analytics is being performed. For example, Fourier transformations in order to find weird frequencies that started to appear because some grain of salt entered your gearbox. So those kind of things, and that's also a big data problem because these sensors produce quite a lot of data. So you can think in order of 20 gigabits per hour per turbine. So the big data problem here is to have real-time turbine monitoring stream and processing and analytics. So, and the reason we did that is to do operation, maintenance, and production based on this real-time sensor data. The fourth pilot, which will also be discussed later on by Luigi and being demonstrated, so therefore I'll keep it brief, is on transport, which is together with CERT, Fraunhofer, University of Bonn, and Ertico. So there the big data focus area is sensor network. So you have roads and they have all kinds of sensors, and using these sensors to prevent traffic jams. That's one of them, to help people to declog the cities and to make it more efficient to use all these resources that are becoming sparse or doing damage to our environment. So what they are doing is they have various data collections sources for data collection, like Bluetooth detectors, etc. And they did a pilot in Thessaloniki in Greece, where they analyze all this data. And it's also a big data problem because to calculate where a person is, what the direction is, how many people are going where, for many cities, that cannot be done on one machine. So you need, it is a big data problem. The fifth showcase is climate, which is done by Democritos also. And there you have, actually, there are two pilots because we have 3 cycles and most people kept the pilots the same during all the cycles. But here in the climate societal challenge, there are actually 2 pilots. One of them was downscaling climate and weather models, which is important to, actually this downscaling process is a big data problem. So downscaling, I have to explain a bit what downscaling is. So climate models, they are simulated by large clusters, and they actually kind of simulate how the climate will look like in 1 year. And in order to do some research with that, you have to query that model to tune it for the requirements that you have in your specific use case. For example, I want to know what is the predicted humidity and water levels in the North Sea in the coming 5 months. It's not just a simple database because these models, they are terabytes big. It doesn't really is also or there's some pollution cloud coming to use the weather, the cloud, the spread of to predict the movement in the atmosphere, to predict where the pollution is going. So you can use wind models in order to predict which parts of the city or which parts of the country have the highest likelihood to be damaged by exposed to this, for example, this pollution. And also do it backwards. So if you find somewhere you have sensors in your country that monitor nuclear activity, so you have some Geiger counters, and then you detect something, then you can use the weather model in order to predict what is the source of this of the pollution. So that's also a big data problem because these models are very large. The sixth use case is social sciences, which is together with Tesla and Semantic Web Company. And there we work on helping people, so researchers, but also citizens who are concerned that all the money is spent wisely. So now more and more municipalities are opening up their data. And sometimes they do it on a weekly basis, sometimes even on a real-time basis, to see where and for what the tax money is being used. So this use case, this pilot, gathers that data and offers a platform where people can get insights for their municipalities where the money is being spent, and in a nice user interface like what you see on the screen. This is also a big data problem because, of course, all this gathering, this information cannot be done on one machine. And we hope that the Big Data Europe infrastructure can do that, and which is possible. So the last showcase is security, which is together with SATSEN, Demokritos, and the National University of Athens. There we have satellite data. You have these satellites going around the world and making a picture of all kinds of parts everywhere. So I think this Copernicus satellite makes pictures from the whole world every day, or at least twice once in the 2 days. And then you can detect changes in the environment on the location. So if you look on the screen, you see there the two snapshots where one is just an empty space, and then you see some kind of structures appearing, which are tents, which were refugees. I think it was from the earthquake, but I don't remember exactly. So part of this pilot is to monitor Twitter feed, social media, and if something is going on, that you quickly can fetch the satellite imagery data and see if there's any changes that support the panic which is on the Twitter stream. Another one is, for example, the earthquake that recently happened in Italy. Then you can see if there's where most likely people got into trouble. So it also helps the rescue people to find quickly, to identify the places which might have been experience trouble. So these were the pilots for each of the 7 societal challenges. I'm out of time, but if you have any questions, please ask me. And I would like to refer also to the YouTube channel from our project where many nice webcasts are being given, demonstrating in more detail all these pilots. And I give back the floor to the host, Simon.
Thank you very much, Ronald. So as Ronald said, there's more information. I also shared in the chat the landing page about the pilots, but now we will have an example from the Societal Challenge for Transport. So we will have Luigi from Fraunhofer, a colleague from Fraunhofer, who will give us a demonstration of this pilot. So we will now switch over to Luigi.
Good evening. I'm Luigi Selmi from Fraunhofer AIS, and we have developed the SC4 pilot for smart, green, and integrated transport with our project partner from the Hellenic Institute of Transport. So the purpose of the pilot was to monitor the traffic status in an urban environment using floating car data. We use the data provided by the Hellenic Institute of Transport, who collects floating car data from the taxi fleet in the city of Thessaloniki, Greece. Each taxi sends a record every 30 seconds about its location, latitude, and longitude, speed, and orientation to a server that is managed by HIT that processes the data for traffic monitoring, analysis, and forecasting. So what we needed for our pilot was an application to collect the data, transform it in a binary format in order to be consumed by another process to match the location of a vehicle with the road segment, and compute aggregation such as the number of vehicles in the road segment within a time window and the average speed. So what we choose as components for our application was Apache Kafka to manage the distribution of the messages, and Apache Flink to process the stream data, and Hadoop HDFS or Elasticsearch for storage. The application was for the data processing have been developed as Flink jobs following the MapReduce programming model, and they have been released as Docker images using the BDE component. All the other framework used in all the pipelines that we have developed for the pilot are also taken from the BDE platform. So this is the architecture, as you can see. But now I'm going to switch to the pilot. As you can see, we can run the pilot in using Docker Compose. I will start it, so after the Flink application we developed, we had to write a Docker Compose file to set up all the components available from the BDE account on Docker Hub, and also define the dependencies for the deployment and the proper initialization of the pipeline using the BDE Integrator user interface. Of course, for this presentation, we have already done the development of Docker Compose or the Docker Compose file and of the initialization. in our case, for example, zookeeper must be available in order to start Kafka, and a Flink master must be started before sending the application to be executed. So as you can see, all the services have been started, and now we can see from the user interface from the browser the dashboard. So in this short time, we present the pipeline that we have used to test the platform and its component to show practically how a pipeline can be started. The map matching has been replaced by a simple match of a vehicle to be within a cell in a 16-cell grid over the city of Thessaloniki. After the pilot is started, we can see the dashboard. And so we can see also that the components used are ready. So Flink, in our case, HDFS, UE to visualize the data. For example, now I had to start my account, where I will see the data that we use as the example data that we will use for the presentation. This is just a sample file of the floating car data that we will process, and we can go directly to the pipeline monitor, where we can see that our pipeline is ready. So we can see Zookeeper, and we can start it. We can see Kafka, and as soon as we click here, we start the broker, and that will create also the Kafka topic, for which the producer and consumer will communicate. Then we set up HDFS. We have already done with the population of the HDFS, and then we also start Flink. We can go directly to see Flink what is doing. So in a few seconds we will see that one application, one job has started, ingestion of historical floating car data. That is finished, as it is a very small one. And in a few seconds, we should see the second job that will apply the map matching in the cell grid, and also the aggregation. So we can go very quickly again back to the UE interface to see the result that is going to be written on the HDFS. So this is written on a rolling file, and the rolling file has already some data. And we can see, for example, that this data contains the first row, that is where we have as the first value the cell ID, then the latitude and longitude, the number of vehicles, and the time step. So as soon as it is processed, the data is written on HDFS. And in another pilot, this data will be consumed by another application, for example, for the visualization of the data on a map. In another pipeline, we have the full implementation of the pilot that it is quite more complex than this. And it can show it can do the proper map matching in the road segment and show the data on the map. For this short time frame, I think this is done, and I'm done with the presentation. So I can go back here.
Thank you, Luigi. So we will proceed to the last part of today's webinar. Which I will take care of. But in the meantime, I would like to remind everyone that you can still ask questions. We will have the last few minutes to answer questions. So quickly, as conclusions. So because it's the end of the project as well, you have learned a lot today about the platform, about how it has been instantiated for the pilots. You have seen one particular demo, and what is the future, how we proceed from here, how will the activities continue. So the final technical contributions I've seen are the Big Data Integrator, BDI in short. It's a platform as a result of the project's activities. What does it offer? It's a starter kit for big data pipelines, making it easier to build your own data pipelines. A minimal standalone system for big data projects, another way to look at it. It offers plug and play, reusing existing open source components. You can also plug in your own proprietary big data components. There's a way how to do that. But the point is we do not recreate any of the popular or existing components. It's modular, it's free, and also it's open source. On GitHub, you can find the source. The main part of the architecture and the platform is it's Docker containerized components. So multiple Docker containers plus easy to use graphical user interface, which is looking more uniform than any other option out there. And you see also the figure on the right here. And the main innovative feature that we have talked about today, which was not available in the previous launch, is this integrated development environment. So I won't go through a repeat of that. It's just to wrap up what was the value of today's webinar, what is the final status of this technical contribution, what's going to happen after the project. So the Git repository, of course, will survive the project. It will be driven by the community, specifically the open source community. There's a number of follow-up projects. You see some mentioned there. There's also some entities or industry adopting these solutions for their own needs. And of course, the community on GitHub will be, we will have a presence as project consortium members. But the maintenance of the platform will be driven by the actual users of BDI. So that's the plan for that. However, we will also plan to meet. We have commitment for the core number of especially technical partners in BDE, Big Data Europe. And we plan to have a series of workshops, semantics and big data, focusing on variety, because this was one of the innovative aspects of the architecture behind the platform. And also one last point, standards. Yeah, we're trying to influence big data standards, so the requirements within the stakeholders. This was very valuable exercise, getting big data requirements from a large number of stakeholders, and this did not benefit only our project. We shared these results, and also the architecture that we defined has been, for example, linked to the Big Data Value Association's reference model for big data. And you can see on the right one version of our platform, how it links to the general structure of this BDVA reference model on the left. And also another way how to see it, if you reassemble our big data integrator platform's architecture components on top of the BDVA reference model, it would look like a bit like this. So you have visualization user interface on top, data analytics and processing architectures beneath that, and data management at the very bottom. And you can see how some of our components and also some of our layers can be fit in there. So the message here is that, sorry, and also importantly, the engineering and DevOps from the BDE reference model includes our support layer, the user interfaces, and also the resource management layer through Swarm. So message here is the results we achieved through the projects, we're trying to, as much as possible, they have already been accepted and endorsed by BDVA in this case at the standardization activities. So we're doing as much as possible to continue the activities in the projects. And I'll use the last minute to say there's the final project activities. There's 2 remaining societal workshops, energy and health. You see the dates here. One is in Amsterdam, one is in Brussels, both within the next 30 days. If you know people who could be interested in those areas, yeah, feel free to join us. We will also be present at the European Big Data Value Forum in Versailles next week. This is a combination of the European Data Forum plus the Big Data Value Summit, which took place yearly. We'll have presence in 4 sessions there: geospatial, transport, energy, and standards, and also we'll have a schedule with demonstrations. And for those of you maybe attending the event, there's a schedule also in the leaflets, which will be in the conference bags. And there's some remaining community-focused online hangouts. You can find information about these on the website. So I will go now for the question and answer session. I leave you with some important links there. Of course, the recording will be put online, so you can share this webinar or view it later, together with the screencast of the entire demo of the Big Data Integrator, the final one. And let's go to answer some questions now. So I will bring up the most relevant questions that make sense for the entire audience, and we'll start with this one. So yeah, we had a question. Except for Flink and Spark templates, do we also support Kafka streams? And I think Ivan can say something more about that in addition to the answer provided through the app.
All right. Yes, so the question was about support of Kafka streams inside the platform, and Kafka is supported in Societal Challenge 6, which was about municipalities data. Basically, if you want to see how different components are used in, like from the code point of view, please just go into our GitHub repository and search for Kafka or Hadoop or Spark. We have 7 societal challenges, and all of the package components, in the first place, we package them because we will use them inside the societal challenges. So to see the real use of the components, just go to the societal challenges. Each of them got a BDI stack implemented. You can take a look at that and see how it works. Thanks, Ivan.
Thank you, Ivan. Then we go to the next question. Jens, I think this is your question. In SANSA, do you implement your own machine learning framework or stack, or is the learning itself programmed or can be programmed using some other different ML framework like TensorFlow?
Yeah, within SANSA, I mean, we are not recreating similar mechanisms as in TensorFlow, PyTorch, and so on. So we support several frameworks. Like I wrote in my answer, we use, for instance, Spark ML Lib which is a standard machine learning library on top of Apache Spark. And we use MXNet for deep learning in the machine learning layer of SANSA. So we rather draw on existing libraries. So the specialization in SANSA is in terms of the data it supports. So it can read in knowledge graphs, for instance, in the RDF format, and then perform all sorts of inference, querying, and analysis operations. But we do not develop our own programmable framework like TensorFlow.
Thanks, Jens. Then next question is, there was a suggestion about Pachyderm and what's the relationship to our initiative. I think Ivan can say something about this. Ivan?
Sorry, I was muted. All right. So regarding Hadoop and Spark on Docker Swarm, we again provide setup on our GitHub repository. And the last work we did just recently is to run HBase on Docker Swarm. It's a bit more complex setup as running it in a standalone mode, and there are a lot of configuration parameters tweaking. It's available in a Docker HBase repository in a distributed folder. You can find the instructions how to deploy it and how to run it. On top of that setup, Infi was deploying Haliart, which is a distributed Drupal store with a SPARQL to SQL translation. And yes, if you have any questions regarding the setup or you run in any issues, just open an issue on the GitHub and I will be happy to answer you. Thanks, Simon.
Thank you. Thank you, Ivan. Then we have another question about the provision of CPU power and storage, and I think here I can answer. So in this project, we did not offer to provide cloud infrastructure, so we just provided the platform and the services, and it was not an objective of the project to also provide any computation power of any sense to deploy an instance of the platform. This is was not part of the objectives of the project. And then we have a question about the link between the platform in the context of the European EOSC initiative. I think Rigo is in a good position to say a few words about that.
Yes, I think this has to be seen in a larger context of most of the scientific institutes going away from delivering valuable knowledge to publishers and then buying them from publishers again for a lot of money. And so I myself was involved in several projects that tried to share corpora for research, and it was licensing issues. So first of all, it's very important that there is this initiative, and BDE is, or the BDI engine is certainly a tool. But then if you look into the special project which takes up the BDE engine, and especially if you look at the SANSA stack, then you can say, okay, I want to have a certain a use of scientific data, and then because of the semantification, BDI can actually store information about rights or limitations and constraints that come with us with certain scientific data, which allows them to use it appropriately. And this will encourage that people will be able to more publish their scientific data accordingly with the constraints they have, because that's one of the biggest questions today is that they just say, oh, we don't know, we can't, let's keep it closed.
Thank you, Rigo. We'll fit in two more questions. So the first one is there an example setup for a distributed cluster, Hadoop Spark, for example, on Docker Swarm? I think Ivan or Hajra can give an answer to this question. Ivan or?
Yeah, I'm
hello.
here. Oh, sorry, Hajra.
Yeah, you can also answer. It's just that we have examples running, like one is Flink running example and other on of Hadoop that you could find on BDE GitHub repository.
Okay, thank you. That was a short answer in the very last question. I think this goes to Ad. So the question is, in what direction would you see the big data integrator evolving into?
So the integrator application, aside from making sure that it always runs as a few potential directions in which it can evolve. So it will of course depend on what projects pick it up, but there's certainly a direction towards giving more fine-grained hints towards users. So we have a backend that understands what you're doing to a minor extent. So a definite extension point is providing more hints towards users of things, how they can combine certain components. And that is something you can actually source with a semantic model, which we've also defined based on what exists on GitHub already. And then another larger direction is probably more interfaces in the way in which we can help people when they're actually deploying things. So more introspection. So now we have HTTP logging, which is understood. There's work that has been done towards monitoring the HTTP logs, but probably it goes a bit further. And then you have the wider set actually of supporting components for technical but less technical people, essentially removing the requirement of having a terminal. That whole space has very interesting implications also for people that don't mind using a terminal. So the supporting direction is probably where it'll go, and most likely towards hinting people what developers, what they can combine and how it's currently running.
Thank you very much, Al. I would say we now conclude the webinar. We're 8 minutes over time, so thanks everyone for attending. Thanks for your patience. We will, as I said, offer this webinar as a recording, so you can watch it later or share it with your network, and also you will have a screencast of the complete demonstration. So thank you very much. I will now end this webinar. Thanks also to all the speakers today. And the links you had on the last screen, you can go through them to get more information about all the aspects covered today. Thank you very much, and have a good evening.